So, may tell me.
Yeah, I think we can start now. Yeah.
Okay. So, dear all, let me welcome you to this 46th session of Math Clinic. Today's speaker is Professor K. Srinivas from the Institute of Mathematical Sciences, Chennai. Professor Srinivas is doctorate in, of course, mathematics from Tata Institute of Fundamental Research, Bombay. His areas of interest are analytic and algebraic number theory, modular forms and elliptic curves, mathematical aspects of cryptography and digital watermarking. Professor Srinivas has published many research papers of obviously high quality and in reputed journals. He has also co-edited 2 volumes of JRMS and recently edited a volume on Hardy-Ramanujan journal. He has guided 3 PhD students and of course visited many Indian and academic institutions abroad for academic collaboration. So with this very short introduction, let me welcome Professor Srinivas to start the session today on number theory and secure communications. Sir.
Yeah. So, thank you, Professor Rana and Dr. Soumya for your kind invitation. It's very nice. So, actually, this was motivated because of the last talk by Professor Ambar Habib, where we wanted to see the applications of mathematics in other areas. So I thought of maybe we can have this also as an application so that, the teachers, they would know, where elementary concepts are used in day-to-day life. All right. Yeah. So, well, cryptography. So let me write it. Number theory, secure communication. All right. So basically, I will be talking about certain aspects of cryptography, which is more mathematical in nature, rather the textbook, cryptography rather than practical cryptography. So practical cryptography is quite different. All right. So what is cryptography? This is basically the science of keeping communications private. Its goal is to secure, communication in the form of a cipher between legitimate users, namely the sender and the receiver. Okay. And it uses a key known only to them. Basically, this is what is cryptography is all about. So we will use some terminology like plain text, for example. So some terminology. So when I say plain text, this is normal message, okay, which may be in English and which may be converted into numerals by means of some dictionary. All right. Usually it is the numbers which are plain text. Okay. The messages are converted into numbers, and we talk about when we say a message, we mean some numbers. All right. A string of numbers. All right. So we will be using plain text. So this is a plain message. And then when it is encrypted, you say that it is a cipher text. Cipher text. Cipher text, that means it's a coded message. All right. And then for coding, a key is used. So we will be using the name key. All right. So this is the process of encryption. Okay, and then we have encryption. And we have something called decryption. All right. These are the words we will be using. So key is the process of encryption uses some numbers that is called keys. We will see by means of examples. So encryption would mean plain text is converted into some coded text, that is encryption. And when the coded text is received by the receiver, the process of converting back into the plain text, that is called decryption. So we will say that the message is decrypted. That means from the cipher text, one gets the original message back. So these are certain words that we'll be using. All right. Okay. There are two types of cryptographic protocols, that means algorithms. One is called symmetric or private key. So private key, or sometimes they call symmetric. Symmetric key cryptography. So in which, both the receiver and the sender, they share the same key to encrypt and decrypt the messages. All right. So that is called private. And it is very important that the key that they use, that has to be kept private. All right. So an eavesdropper or an unintended receiver shouldn't be able to catch hold of the key, because if they have the key, then they can, decrypt the message. All right. So therefore, it is called private key because the keys are supposed to be kept secret. All right. For example, we have this famous Caesar cipher. Example. So Caesar cipher or substitution cipher, where you send x, convert x by shift x by some number k. We have 26 alphabets. So let's say A represents 1 and Z represents 26. So this is modulo 26. So k is some number, let's say 3. So each letter is shifted by 3 places, let's say. So this is one type of cipher. So this is the plain text. X plus k is cipher text. And this k is key. All right. So when x goes to x plus k, this is called encryption. When it goes to the receiver, and if the receiver also has k, the number k with them, with him or her, then they can decrypt. So once they receive y, what they will do is y minus k. Okay, to get back the original message. All right. So this process is called decryption. So this is a decryption. This is encryption. This one is encryption. All right. Now suppose each letter is shifted by some number. All right. Let's say A, it's going to Z, let's say, and B is going to D, and so on and so forth. All right. Therefore, now the question is, how difficult is it for somebody to get this one? How difficult for an adversary, to get hold, if suppose one sends a message, okay. So the question is, how many distinct this simple substitution ciphers are there. Okay. All right. I hope the question is clear. Each letter is shifted by is changed to some other letter. All right. So A has 26 choices, B has 25 choices, and C has 24, and so forth. So therefore, there will be 26 factorial substitution ciphers in total. All right. So if B sends a message to A, and suppose an eavesdropper E wants to intercept that and tries to recover the message. All right. So then, how many times Eve has to try? That is 26 factorial. All right. So suppose, so what I'm saying is, suppose Eve. So usually our characters are A, that is Alice, usually the sender or the receiver. These are standard characters in cryptography. Bob, that is B, is a sender of the message. And Eve, eavesdropper. That means an unintended receiver who wants to, who can access the message and wants to decrypt the message, all right, by all possible, combinations, guesses, all right. So Eve intercepts, let's say Eve intercepts one of Bob's messages, all right, and she attempts to decrypt it. All right. And by trying all possible substitution ciphers. So this process of trying without knowing the key is called cryptanalysis. All right. These are certain languages. So how long it will take for Bob, for Eve? All right. And suppose Eve has the capacity of trying, let's say, to check 1 million cipher text, cipher alphabets per second. We usually assume that the adversary has a lot of power. Suppose Eve is able to check 1 million cipher alphabets per second. All right. Even if you give this much of power to Eve, then also it would take her more than 10 to the power 13 years to try them all, to try. All right. So this is exhaustive search. Okay. But as you know, the age of the universe is about 10 to the power 10 years. Therefore, one can think that, this substitution cipher is pretty safe. All right. But that's not true. All right. So it's very puzzling that, this can be broken quite easily. Because in English language, there are certain letters which occur very frequently. So something called frequency analysis. So the people who analyze cryptographic protocols, they are called cryptanalysts or cryptanalysis. The study is called cryptanalysis. Okay. By using frequency analysis, that is frequently, because we can assume that the message is in English text, and the most frequently occurring letter is E, followed by T, then followed by A, O, N. So by, looking at this and making a table of frequently occurring, letters, it is quite easy to get the cipher to a plain text from the cipher text without even knowing the keys. All right. So this is not at all secure. And moreover, you see here, each user is given one key. So the receiver and the sender, they have to have the same key. All right. So there is a problem of key distribution. Because suppose there are, so the problem of key distribution. Suppose there are 10 users, and then how many keys are required in order to have this system work? So that is 10 choose 2. All right, which is 45. All right. So when the number of users is too much, okay, too many, then this becomes, the key management becomes a very big problem. All right. So this is not, a very good one in that way. All right. So therefore, there was a need for something which will not allow you to keep the keys. I mean, so therefore the problem is, so the main problem how to securely transmit the keys. Right. Once both the sender and the receiver have the same keys, they can easily encrypt and decrypt. So one way of doing encryption and decryption, what they do generally is, so you have a message, let's say M. All right. And let's say it has an n bit number. That means it's a string of n digits. And let's say that they are binary digits, so 0 or 1. All right. So let's say 1 0 1 1 0, something like this. Let's say this is plain text. Okay. And K is the key, and this is another number. Let's say 1 1 0 1 0. This is M, and this is K. The most efficient way of encryption is just to take the XOR of these two, exclusive OR. Okay. So it is modulo 2 addition. All right. Where the carries, the carry is not carried to the next number. For example, 0 XOR 0 is 0, 1 XOR 1 is 0, 1 and this is 1, and 0 and 1 is 1, and this is 0. So this is the ciphertext. All right. And now this goes to the receiver. Okay. So 0, 1, 1, 0, 0. This, and suppose the receiver also has the same key, 1, 1, 0, 1, 0. All right. So the receiver will XOR it again to get the, this is the original message. All right. So, and if the message is long and the key size is as big as the message, all right, this way of encryption, this way of doing encryption is provably secure in the sense that it is the most secure way of communication. All right. But again, the main problem is how to send the keys to the various parties. If you can securely send the keys, you can as well send the message itself securely. All right. So the main problem is how to securely communicate, transmit the keys to the receiver or the sender, between the two parties. That is the main problem. And that problem was addressed by what is called public key crypto system, which is the main topic of our talk today. So public key crypto system. All right. So this was in 1917. This started in 1917. And in this, each user is given two keys. So one is private and the other is public. Okay. So if M is a message, yeah.
So this vertical encryption is not secure, right?
No, it is. I mean, once you can send the key to the person, then it becomes it's very efficient. In fact, most systems, they use a symmetric key encryption.
No. This symmetric key, MZOR key.
Sorry. Hello, Arvind.
These,
I think your
yes,
audio
sir.
is not clear. So please put your question in the chat box.
Yeah. All right. So each user is given two keys. All right. Let's say A is one user and B is another user. Okay. So there is a public key and there is a private key. All right. And similarly, E of B, D of B. All right. By using this public key is known to everyone and private key is known only to the party. DA is known only to A. Similarly, DB is known only to B. Okay, we will see the examples later, little later. All right. Okay. Then, if M is a message, all right, and A wants to send a message to B, B knows the public key because everyone knows the public key. Okay. So A will encrypt this M with the public key of B. Okay. So let's say E of B. This is the encryption algorithm. All right. And then he will again encrypt with his own private key. Okay. DA. All right. This is what goes to B. All right. Now what B does, this is a completely different number than M. All right. Now B knows his own private key, and B knows the public key of A. All right. So to this, he will first apply, the public key of A, that means E of A, D of A, then your E of B, M is there. All right. So you see this was the thing. Now E of A and D of A, suppose they get cancelled. All right. Then what it will give you is E of B, M. All right. E of B is gotten from the public key of B, and B knows the private key, his own private key. So then you will apply D of B here, all right, to this. Now D of B and E of B, suppose they get cancelled, then you get M. Which means, this encryption and decryption are the inverse of each other. So in order that this system should work, make sense of this protocol, one should have E of D of M is equal to D of E of M should be equal to M. That means E and D should be inverse of each other. That is, E and D are inverse of each other. Okay. And other thing is that since E is public, from E one should not be able to find D. A third person should not be able to find D. Otherwise, they will decrypt it easily. All right. The knowledge of E, encryption, shouldn't give information, or the knowledge of public key shouldn't give information about private key. These were the issues, Okay, and these were addressed, and these were, very beautifully done by means of application of simple number theory. So this was first done by Diffie-Hellman in 1976. This was Diffie and Hellman. They proposed a scheme. Okay, this was the first invention of public key cryptography. Okay, where they say that give each user 2 keys. Okay, you encrypt the message with your own private key and the public key of other, and the other person who receives, they will decrypt it with their own private key and the public key of the sender. This is the, all right. Okay. And based on this Diffie-Hellman's thing, a modification of that, all right, was done by later in 1978, this RSA was invented by Rivest, Shamir, and Edelman. All right. So basically, the problem is we want a function All right. Let's say F Z to Z such that, or from some group to another group such that F is easy to compute, but F inverse is difficult to compute. Because E and D are inverse of each other. Okay, E should be easy, but D should be difficult from the knowledge of E. Okay, so people were looking for this kind of functions. The one way is easy, but the inverse is difficult. So one such function was, examples of such function. Given two large primes, P and Q. Construct the function f of P comma Q as P into Q. All right. Let's say this is N. So given P and Q, multiply those. This is a one operation. All right. But given N, F inverse will be is nothing but P and Q, the factors. Okay. Okay, these factors. And it is believed that factoring large numbers is difficult. Okay, this difficult is a technical term. All right. For example, what is the most naive way of factoring a number? All right. So for example, you are given a number N and you want to find factors of this.
Srinivas,
Yes, sir.
just wanted to ask you, there are some questions coming up. Would you like to take them along?
Sure. Yeah.
Or would you like to take it later on?
No, I can take it right away also.
Okay. So the first question is, somebody was trying to ask, but the audio was not clear.
Yeah.
So can you read the chat box or shall I?
Yeah. So one is 26 factorial, right?
No, below that, if
If
there is for two messages.
and the mentioned symmetric key encryption is not secure. What is that?
I don't know. This is the question which has been put up.
Okay.
Yeah, so sir, I'm audible.
Yeah, but your echo is coming in your audio. That's the problem.
What is this thing?
Okay, so there is another question.
Uh,
E of B and D of A are inverse. So the E and D of A are inverse to each other. Similarly, the D and E of B are inverse to each other. All right. So this is the answer to the third question. All right. So second question I will answer after after I talk to you later. After that.
okay, fine. Please go ahead.
Yeah. All right. So the the most naive way of factoring a number is to look for all primes up to square root of n. You see, collect all primes, see whether they divide n or not. Because if a number is composite, then it will certainly have a prime it will have a factor which is less than square root of n. Okay, less than or equal to, because both these numbers cannot be strictly bigger than square root of n. A and B cannot be bigger than square root of n, because if they are, then the product will be bigger than n. Therefore, at least one of them will be less than or equal to square root of n. So this way of factoring, finding factors, you have to collect all the primes up to square root of n. All right. And then divide it and find out whether it's a factor or not. So these kind of, how many steps are required? So at least, p to the power, half, n to the power half you have to go. Okay, these many numbers you have to try in the worst case scenario. All right. So in computer science language, you say that something is easy or efficient if, whatever algorithm that you're using, it takes the number of steps is a power of the input size. What do you mean by that? So if n is an integer, the input size of n is the number of digits in n. All right. So let's say this is a0 plus a1, 10 ak, 10 to the power k. So there are k plus 1 digits, let's say. So you see, n is less than or equal to 10 to the power k plus 1 and bigger than or equal to 10 to the power k, right? So you can find a bound of number of digits in terms of n. They are about log n. So input size is, so input size, the size of n, we say that size of n is log n or O of log n, we say, okay? When we don't want to bother about the less than 2 times or 3 times or constant times, we don't bother, then we say that log n. So you say that f of x is O of g of x if fx is less than or equal to some constant times g of x as x goes to infinity. Okay. So this O symbol is like this. All right, O symbol means. Okay, so now the naive way of factoring numbers is takes n to the power half. This is e to the power half log n. All right. So it is exponential in the input size. All right. So such algorithms, such method, this method, we will say that it takes long time or exponential time algorithm. All right. Okay. So therefore, factoring a number is difficult. All right. And based on that, a cryptographic protocol is devised. So based on the problem of difficulty of factoring integers, RSA system was created or invented. Okay. Okay. What is, so for RSA system, one uses a very nice theorem, which was of a lot of theoretical or aesthetic interest in number theory. So let's look at this FP or ZP. So these are integers 0, 1, 2, 3 up to P minus 1. All right. P is prime. All right. So if you look at the non-zero integers of FP, they form a group under multiplication. All right. So we say that ZP star, this is 1, 2, 3 up to p minus 1. Forms a group under multiplication. Okay, that means you multiply any two elements, the resulting number will again be in ZP star, and each element has an inverse. All right, modulo P. All right. So this forms a group, and there is a very nice, result in algebra, which says that in any finite group, you take any element A, raise it to the power order of the group, what you get is the identity. So that in general, A to the power order of the group is identity. All right. If G is a group, A to the power order of the group is identity. So in this particular case, if you take any A belonging to ZP star, so this is not very difficult to see, okay? ZP star, then A to the power. Now the order of this group, that means the number of elements in this group is P minus 1. So A to the power P minus 1 is congruent to 1 modulo P. So for all A and P co-prime, or P does not divide, take any A such that P doesn't divide A, then A to the power P minus 1 will give you 1 modulo P. And this is known as Fermat's little theorem. Because Fermat's last theorem is something that was recently proved, namely x to the power n plus y to the power n is equal to z to the power n has no integer solutions in x, y, z if n is bigger than or equal to 3. That's the last theorem. This is Fermat's little theorem. All right. And as a generalization of this, if you look at z, take any n and zn star. That means these are set of all elements A less than or equal to n and A co-prime to, relatively prime to n. This forms a group, multiplicative group. All right. So these are all, elements. So from 1, 0, 1, 2, 3, 4 up to n, look at all elements which are co-prime to n. All right. And phi n is nothing but in the Euler-Totient function. By definition, this is number of integers less than or equal to n and are co-prime to n. That means from 1 to n, pick out all numbers which are less than n and which are relatively prime to n. For example, if n is equal to 8, then you have 1, 3, 5, 7. These are the elements which are less than 8 and which have no common factor with 8 other than 1. All right. So as a generalization of this, since this forms a group, take any element A in this group, and what is the cardinality of Zn star? That is nothing but phi n, right? Because the number of elements less than n co-prime to n, such they are phi n in number. All right, as Zn star is equal to phi of n by the same theorem, namely take any element, raise it to the power order of the group, you get identity. What we get is if A and n are co-prime, then A to the power phi n is congruent to 1 modulo n. All right. So this is known as Euler's theorem. This has many beautiful applications. All right. Which I will not be having time to discuss great details about these things. But anyway, so what does RSA, Rivest, Edelman, and Shamir did? So they looked at, take a large number n, take a number which is product of two large primes. Okay. Compute phi of n. Now phi of n is nothing but number of elements which are co-prime to n and less than n, right? So this is phi of p and q. So yeah, we will leave it here. Okay. Now choose a number e which is co-prime to phi of n. All right. Now, there is a very nice theorem, nice result by Euclid's algorithm. It says that if A and B are co-prime, if they don't have any common factor, then we can find integers x and y such that ax plus by is equal to 1. It's always possible. All right. This implies that ax is congruent to 1 modulo b. All right. Okay. So whenever A and B are co-prime, you can find x that ax is congruent to 1 modulo b. But ax is congruent to 1 modulo b is nothing, means that x is the inverse of A modulo b. So since E and phi n, we can choose E, which is co-prime to phi n. All right. So we can solve this congruence, Ex congruent to 1 modulo phi n by Euclid's algorithm. All right. Let's say x is equal to d. Say Ed is congruent to 1 modulo phi n. All right. Okay. Once we have this, now what is the encryption? So our message is M, plain text. Let's see. The encryption of M, okay, is done by means of M to the power E modulo n. This is the encryption algorithm. Okay. Now, corresponding to this encryption, the decryption procedure is given as follows. So if you input any y, so the decryption algorithm, what it does, it raises y to the power d, where this d is same as inverse of E, okay? All right. So this is the encryption and this is the decryption. Now the claim is encryption and decryption are inverse of each other. That means d of E of M is nothing but M. Why is that? So what is E of M? E of M is M to the power E. Right. So d of E of M is d of M to the power E. But what does D do? D raises anything. Why any input you give, it will raise it to the power D. So D of m to the power E is nothing but m to the power E to the power D modulo n. All right. This is m to the power ED modulo n. But ED is nothing but E is the inverse of D. So ED is congruent to 1 modulo phi n. As ED is congruent to 1 modulo phi n, this implies ED is equal to 1 plus some integer times phi n. All right. Therefore, D of ME is m to the power ED, you substitute 1 plus k times phi n modulo n. And this is nothing but m to the power k to the power phi n modulo n. This is same as m to the power phi n to the power k modulo n. All right. Now m is a message and n is product of two large primes. So what you can do is always in practice, m can be taken. So one can easily choose m to be smaller than the, the minimum of PQ. All right. So that m will be co-prime to n because n is the product of PQ. So if m is smaller than P and Q, then m will be co-prime to n. So if m is co-prime to n, then m to the power phi n, as m is co-prime to n, by Euler, m to the power phi n is congruent to 1 modulo n. And therefore, this will be equal to 1. And hence, D of ME, thus D of ME will be congruent to m modulo n. All right. But since m is smaller than n, this in fact means D of m to the power E is equal to. Okay. Therefore, you see, this is how decryption is done. So if you take any cipher text C, this is how decryption is done. All right. So this is the, way that was given by reversed RSA. This is what is RSA algorithm is all about. Now, few minutes about the security of it. I will not have time to discuss about Elgamal and other things, unfortunately. So the thing is, why is it secure? Okay, what is the security aspects of it? All right. Now, the thing is, see, from m to the power E to get m, one should know D. Because if you raise it to the power D, you get m that we have seen. All right. The other way is, m to the power E is known because it's a ciphertext which is in the public domain, which is going through some medium. And to get m, you need to find eth power. All right. E is also known because E is the public key. So m to the power E is known, n is known. Can we find m? In order to find m, either we find eth root, but finding eth roots in a group is difficult. All right. And therefore, the easiest thing is to raise it to the power d. Therefore, the entire security depends upon finding d. And you see, d is a solution to this phi n. All right. So one can solve for x provided you know phi n. All right. But phi of n, which is phi of p times q, it so happens that this is p minus 1 times q minus 1. Phi is a multiplicative function. It is equal to phi of p, phi of q. And phi of p means the number of elements which are less than p and relatively prime to p. They are p minus 1 in number. And similarly, phi of q is q minus 1 in number. So you need to know, in order to know phi n, you need to know p minus 1, q minus 1. In particular, you need to know p and q. That means you should know the factorization of n. And the assumption is that factorization is difficult. Factoring large numbers is difficult. So the entire RSA, the security of RSA lies in the assumption or in the belief that factoring large number is difficult and therefore it is still secure. But the thing is, one comment I would like to make before I stop it is that this is a very expensive method. That means it's very slow. All right. Therefore, these messages that you pass are short. They should be short. So RSA is used to send keys to the parties through insecure medium, through our, through internet or, through anything. The keys are transported by means of RSA system because it's a very secure system, all right, even now. But because of slowness, messages are not communicated using RSA protocol. Only keys are given, keys are shared between the parties. And once you have a key, you can use the symmetric, encryption because that is very fast and efficient. All right. So all, our mobiles and, lightweight things, they use symmetric key encryption. All right. And decryption. Whereas the keys are passed through RSA. And then there is another one called El-Gamal. And then there's another one for exchanging keys. That is Diffie-Hellman, key exchange protocol, which uses the difficulty of something called discrete logarithm problem in groups. I don't have time to discuss, so I would rather wait for any possible discussions and comments.
Thank you, Srinivas.
Yeah.
Anda, is your question which was not clear, you still want to ask that question? If your audio is okay, you can unmute and ask.
Yeah, so am I audible?
Again, that
Yeah. Okay.
I have some notes of this. Those who are interested, they can write to me. Okay, I can share the notes. I will give you more details.
Professor Nair, would you ask?
Professor Srinivas.
Hi.
Good evening. No, mine is very simple query. In this process of decryption, you used only n and phi n, but not exactly the 2 primes as such. It can be done with more than 2 primes also?
Well, once you have E and D, one should destroy the primes. All right.
Okay.
So the security depends upon factorization. So one should not keep the primes. All right.
Okay.
Now, if you have more primes,
Yeah.
if you have only 2 primes, factoring
Yes.
n by trivial way would entail you to look for n to the power half numbers, right? Because
Okay. Yeah,
If
right.
you have
Yeah.
too many prime factors, then you don't have to search a bigger space. Suppose you have 3 prime factors of n, then n to the power within 1 to n to the power 1 by 3, you can find a factor. If you have 5 prime factors, within n to the power 1 by 5, you can find a factor. So the security will become slightly lesser.
Yeah,
Yeah.
more complicated. Yeah. Okay.
Yes.
Okay, good. Thank you.
Hello, sir. Is it fine? But in addition, I need to add, like, there are some literature that exists that n equal to for p raised to p square q for RSA, and there are also crypto system that kind of p raised to r q raised to s kind of thing.
Well, there are many systems, but this is the textbook.
This
Right.
in textbook RSA is PQ, but
Yeah.
these are variants of
But other thing,
RS.
other thing is that in practice, it is not used exactly in this way. You have to pad it, and
Exactly.
you have to do several things. Right? So one
Because
can,
RSA is
yeah. Yes. So there are one nice reference I would like to give you is some So references one can look at.
Your notes you are saying you can put in the chat box if they are available somewhere.
I need a little bit of addition of that. Right? I need to edit it a bit.
Okay,
I
fine.
don't want to publicly share right now, but privately I can share. Right?
No, I think people can mail you and then request you.
There's a good book, Koblich's book, Number Theory, a course in number theory. And cryptography. Those who are very serious look at about cryptography, they can look at book by Managers or and Waston. This is Encyclopedia of Cryptography and Security. Yeah, there are many other nice articles by Bonet.
I have shared your email anyway in the chat box.
Yeah, sure.
So people can get in touch with you for any other query or help
Sure.
or suggestions or discussion they want to do it. Anybody else has a question or a suggestion or a query? I just wanted to ask you one question which is not directly related to this. You see, when in the barcode, first few letters are given by some company, some agency to the business person. So they also use cryptography, right?
You are talking about barcode?
Yeah, in the barcode, the first digits.
Yes. Yeah. So the barcode, the numbers, see, for example, the simplest example, let us take our, this number, credit card numbers, let's say.
Yeah.
So there is an algorithm to create the credit card numbers. All right. And the last digit is called the check digit. So suppose, so there is very nice, I forgot the name of that algorithm, but you have to multiply the first digit by a number, second by another number, third by another number. There is a way of doing this.
Right.
And the last one is the checksum. So the moment we enter it, it will immediately see whether the checksum matches or not. If it doesn't match, immediately it will reject.
Right.
Similarly, RFID codes will use the symmetric key. All right. Symmetric key crypto system because they're very fast. They have to be very fast. So very interesting area, in fact.
Yeah. Anybody else has a? If not, let me thank Srinivas for
Yeah.
bringing real world into the mathematics world and making it so nice and elegant that everybody gets probably inspired to look for more material on this. So, thank you, Srinivas, for your beautiful lecture.
Thank you
And
for attention.
inspiring.
Bye-bye.
Thank you, everybody, for coming over for this session, and take care. Thank you very much.
Thank you.
Soumya, anything you want to add?
Yeah, thank you, sir.
Thank you, Soumya. It was
Yeah.
Thank
nice.
you.
Yeah.
Sure. Okay.
Okay.
Take care, everybody.
Bye.